So Professor Arnan Mitchell, he's from RMIT at Melbourne, Australia. So I think probably he's the one of us that has traveled the farthest to come here. So we really appreciate you joining us for the conference. He's a distinguished professor at RMIT, and he's also the university director of their micro-nano research facility, and also the director of a brand new center they have, ARC Center of Excellence for Optical Microcombs for Breakthrough Science, the COM Center. He's been working on, in addition to data communication, to designing on photonic devices, and it's a very big breadth of work. But I think today he's going to talk on their microchip development and using light, sound, fluids, and electronics for data communication. So please, let's join me in welcoming him. Thank you.
Thank you very much. So, thank you very much for inviting me to this. I've got to say this is a little bit outside my field. I'm mostly a photonic chip person, and we're exploring the opportunities for underwater, but I have a lot to learn, so I look forward to talking to you all about that opportunity. I'll probably spend maybe 60 to 70% of this talk introducing some of the work that we do and the COM Centre itself. It will eventually arrive at Neuromorphics, and I think will complement some of the things that we've heard about already. So let's see how we go as we go. So the first thing I should mention is I'm from RMIT. RMIT is actually a pretty big university in Australia. It's got about 90,000 students, and unusually, and I've tried to expand Google Maps to its largest so that we could actually see where we are in reference to where my home institution is in Melbourne. But it's right in the middle of Melbourne City Central Business District. And so you can see this is a shot of Melbourne, and you can sort of see, let me just put my laser pointer on. Here we go. You can see the RMIT logo there. This is Melbourne Central Railway Station, and that's my office there. So it's quite close to the centre of the city. We have, you might wonder, okay, why have I travelled almost entirely around the globe to come here? And how did I get involved? So RMIT has a research office in Barcelona called RMIT Europe. It's been running for at least 10 years, and it specialises in coordinating sort of European Union actions, particularly doctoral networks. And so one of the things, actually, another thing I've been doing while I'm here is a doctoral training network, particularly between France and Australia, but not to be left out, we have also put in a postdoctoral training network between Spain and Australia. So that's just sort of coming together now. It's just been awarded, and we're looking forward to particularly working with Navantia on that project. So my own research team at RMIT is the Integrated Photonics and Applications Centre, and basically it sort of has an engine room, which is sort of the design, fabrication and packaging of photonic chips. And I get very excited about these photonic chips, but to most other people, they're fairly dull because they're sort of these little grey squares with features you can't see on them, and they often work on light that you also can't see. So that's very hard to get people excited about. So we emphasise the applications, and I'll go through some of the applications in a little more detail. So running that engine room, I have a design expert called Tuc Nguyen who does all of our simulation and theory and design, and then the fabrication team is run by Guanghui Ren. Probably our team at RMIT is about 50 people, so it's a pretty big group of people, and maybe a third of them are sort of in this engine room. And essentially what they do is they create designs of integrated circuits using laser light, and then we make prototypes. And we have all the facilities actually in the city at RMIT to fabricate these chips as well as design them, and package them, and then put them into a format where we can potentially use them. We work on silicon, which is sort of the industry standard, and silicon nitride is emerging as industry standard. But one of the areas we really specialise in is lithium niobate. And Lithium niobate is quite interesting. I've been working on lithium niobate since I was a PhD student, and it's interesting because it actually has acoustic properties. It can be used for surface acoustic waves and piezoelectrics. It has RF properties. It's sort of the interface between analog RF and laser light. And it's also really good at photonics, and it can convert light from telecommunications wavelengths to visible, and it works all the way from ultraviolet into the mid-infrared. So this is pretty exciting. It covers, I think, all of the areas that we heard about this morning for underwater communications. So, it seems like a pretty good platform. We're interested in trying to make quite complex integrated chips that deal with laser light, acoustics, and RF all in the one package. The idea is that if you can integrate them together and package them, that can be more robust, which I think would be quite important if you're sort of operating, sort of deep in the ocean, actually having not a lot of moving parts. Everything's integrated into a monolithic chip. Okay, so that's enough about the chips themselves. Let's talk about some of the applications. So very briefly, I knew that there were going to be some people talking about soft robotics today. So I wanted to say just a few words about our biomedical team. That's led by Cesar Huertas, who's actually did his PhD in Barcelona. And he runs this team. And this is a sort of an example of a chip that we have. So this is the photonic chip you can see here. Each of those little squares actually is a sensor, and you've got, it's a Mach-Zehnder configuration, so you've got a reference arm here, and then a sensing arm, which is a big coil. And you functionalise that sensing arm with antibodies to whatever you're trying to sense. And as the thing that you're trying to detect attached to the surface, you can actually measure the phase change that you get with that. One of the applications we've done in collaboration with ICN2 here in Barcelona is looking at antibiotics in seawater. So when people farm, the antibiotics they use run into the rivers, and that runs into the sea, and you can measure trace amounts of antibiotics actually in the ocean. So that's one of the things that we were working on. This is another example. So we marry those photonic chips with microfluidics. And so this is an example of one of our active microfluidic devices. You can see there's pumps and valves and active fluidics going on there. This is all made with a one-shot injection mold. So it's sort of a technique that we developed, and we're able to sort of design something like that and actually be fabricating prototypes in a couple of hours. So it's really, really good for rapid prototyping. And this particular chip was used for looking at blood clotting, for example, but you could imagine how you might adapt it for sort of soft robotics. Okay, enough on that. Another team works on sensing and metrology, and this is probably closer to the area that might be interesting for underwater. This is led by Andreas Boas, who used to be a postdoc with us at RMIT, but has since moved to Adelaide University. So this team looks at things like LiDAR, so using laser range finding and then forming that into images. We also look at things like gyroscopes, and so movement sensors. And if you put those, you can imagine if you've got a drone that's flying around trying to create a point cloud, as the drone's moving, that point cloud's, all the points are going to be deregistered. So if you can actually keep track of how the drone is moving, you can re-register all those points and actually get a good image. The third ingredient, if you actually want a proper positioning and navigation system, is time. And so we're also working on trying to sort of integrate optical atomic clocks into these things. So if you don't have access to GPS, you can potentially have all of those things integrated together. And again, this is something that's very important if you're trying to sort of operate underwater. So these are three Australian companies that we're working with. Baraha for LiDAR, advanced navigation, do a lot of the work on inertial navigation systems using gyroscopes, and Quantex is a company started up in Adelaide looking at integrated optical atomic clocks. All right. The last application area that we look at is communications and a little bit of information processing, and this is really where the sort of neuromorphics come in. This is led by Bill Corcoran, who's based at Monash University, and one of the things we have done is really focus on these things called microcombs, and I'll explain what an optical frequency comb is in a moment, but suffice to say that this is a picture of a microcomb. So basically this big disc in the back is a Australian $2 coin. It's one of the smaller coins in our repertoire. Most of us don't usually use coins anymore after COVID, but there's one anyway. And this is the chip, and you can see just in the corner of this chip there's a little ring. That's what it is here. So it's less than 1 millimetre across. And what happens is if you put one laser wavelength into that ring, what comes out is maybe 100 laser wavelengths, all equally spaced in the communications band that you can amplify with an erbium depth fibre amplifier. And so this is sort of an image of that spectrum here. So you can see this green area is the area that you can amplify, and there's about 100 comb lines there. And so what we did was we basically took each of those comb lines and used it as a communications channel. And the quality of the comb lines, they're very, very low noise because of the way they're formed, and they're very, very uniformly spaced and very stable. So you can pack a lot of information in to each of those channels, and so that's what we did. This is a what's called a constellation diagram for communications, where each of those little dots is sort of like a symbol that you can use for communication. So instead of ones and zeros, you can have lots and lots of different symbols, and one axis is intensity, the other axis is phase, and so you can pack a lot of information into each what would be a bit, and achieve a very, very high data rate. And so back in 2020, we actually achieved the world record communications link between our university here at RMIT. We've got a dark fibre that runs between RMIT and Monash under the city, out into the suburbs, and then comes back again. And so we demonstrated 50 terabits per second over that standard fibre that has been in the ground for 30 years. Nothing special about the fibre, it's just the power of this very, very stable microcombs that we were able to achieve. And that got a lot of attention, and on the basis of that attention we applied for this comb centre. And this is the biggest bucket of money that we can get in Australia. So the Australian Research Council funds these major initiatives for 7 years and offers $35 million, so about $5 million a year to really do something substantial. There's 8 universities that are involved in that, and each of the universities put in a similar amount of money. So we were, between us, have about $70 million Australian, which is significantly less in euros, to see what we can do with these microcombs. So just a little bit about what is a frequency comb and then what is a microcomb. So optical frequency combs, they're invented in 2000, and essentially what they are, they're like a clockwork. And so lasers are really good at measuring things, and particularly they're used for measuring distance and for measuring time. And by measuring time, they're essentially used with atomic species and trying to measure the energy difference between different electronic levels in atomic species. And these are those atoms are the same all around the world, so you can use that as a reference. A good example is cesium or rubidium. You can use as these references. But the issue is that you can't actually measure that oscillation frequency directly. You can see the colour of the laser, but you can't actually measure what is the frequency directly. So the optical frequency comb basically gives you a whole array of these lines, and if you beat 2 of those lines together, you can actually measure that electronically. So they can be 10 gigahertz or 100 kilohertz or those sorts of frequencies, but that are accessible with electronics. And so what that means is that if you can tune your laser and then measure the beat to one of those lines, you can actually get a direct measure that you can measure off with electronics of what the frequency is, and that's sort of the power of these optical frequency combs. You can also turn spectra, for example, in the mid-infrared, into an electronic measurement as well. And so this is a way of actually doing spectroscopy, for example, for gases in the atmosphere. So this was regarded in 2005 as sufficient to be awarded the Nobel Prize in Physics. And so you can see John Hall here and Ted Hench standing next to optical frequency combs. This is Scott Diddams, who's part of our centre, looking at a frequency comb that he put together for astronomy. But you'll note that they're quite big. They're sort of about the size of a fridge. They cost about $1 million each, and in general, they need constant maintenance. About every 2 weeks by sort of PhD qualified people who really know what they're doing. So perhaps, because of that, you'll find them in a lot of very specialised laboratories, but they aren't really suitable for deployment. And you certainly couldn't imagine having one of these on one of the drones that we just saw before. And this is our science communicator standing next to one in Adelaide for scale. So about 10 years ago, it was shown that you could achieve these sorts of frequency combs using microchips. And what we've seen recently is that while it's been possible to make photonic chips for some decades now, the semiconductor industry is actually starting to really take these up and make them at scale, because of the adaptation of artificial intelligence, the amount of information that data centres are having to move around. The only way to do that is with photonics, and so they need to actually be putting photonics on the computer chips that are actually doing the processing to get the information off fast enough. And so we're looking to sort of jump on that opportunity and actually use the ability to mass manufacture these photonic chips as a way of being able to make these optical frequency combs generally accessible and hopefully manufacturable at scale. So our centre is half the science and technology of frequency combs and half the applications. And so some of the areas of applications are sensing and measurement, spectroscopy and microscopy. We've got a little bit of work on astronomy, but also information and intelligence. And so there's high-speed communications, but also trying to do some information processing, some filtering, some pattern recognition, before the light, a lot of these sensors are light-based. If there's all this information coming in the optical domain, can you process that before it actually hits the computer, or help the computer in some way? So a few examples. One of our researchers is a seismologist, and she's using these optical fibres to measure earthquakes, actually. So there's optical fibres that are already in the ground used for telecommunications. If you listen to the echoes of the laser light that's sent down those fibres, you can actually see if the fibre's being stretched or compressed, and you can actually see the earthquakes arriving. You can also see other things, like you can see lightning strikes, or you can see the rain falling, or water flowing in pipes. You can measure how full those pipes are and how fast the water's flowing. You can see cars driving over roads, and trains and trams, and even foot traffic. So you can imagine how you could use these sorts of measurements for early warning of an earthquake arriving. You can imagine how you could use these for management of drains during floods, for example. So the issue, though, is that the amount of data that's being generated by even one of these fibres is vast. It's terabytes every day, and Megan Miller's laboratory actually is a supercomputer, and it takes her several months to actually process all the information to see what the earthquakes are doing. And so what she would really like is to be able to do that in real time. And so what we're looking at is trying to use with these microcombs to actually process the information so that it's easier to detect. And I'll say a little bit about how we're doing that in a moment. I won't say too much about the astronomy, but essentially what Jean Brodie, who's an astronomer, is trying to do is look for Earth-like planets in sun-like stars in other star systems. So the way you do that is by looking at the colour of the star, and as the planet is going around the star actually wobbles back and forth very, very subtly, and it changes its colour because of the Doppler effect. And so you're trying to measure that change in colour, which is very, very small indeed. So But the issue with that is that it takes years. So it takes a year for the planet to go around the sun, and so you're looking for this oscillating colour shift that might take 10 years to actually measure. And the issue with the frequency combs is every 2 weeks they're being maintained and recalibrated, and so you don't have a stable reference. And so what she would like is a sort of consumer electronic type frequency comb that would last for decades without any sort of maintenance. And so again, this is the sort of thing that you might like in an underwater system. The last example is Kishan Dalakia, who's working on spectroscopy, and he's sort of a microscope expert, and he's looking at sort of living organisms using sort of advanced microscopy techniques. And we can think you can use optical frequency combs for both spatial imaging, a little bit like LiDAR and sort of image formation, but also spectral analysis, so being able to sort of understand the sort of chemical properties of the specimens. But the issue for him and the issue for us in this room is that most of the frequency combs that we work on have been developed using telecommunications technologies, and so they work at infrared wavelengths around about 1.5 microns, which water is quite absorbing at. And so most living organisms are in water or made of water, and he really needs them at sort of visible wavelengths. So that's one of the things that we're really looking at, is trying to shift these frequency combs from the telecommunications band down into visible and even into ultraviolet, which is important for some of the spectroscopy, but also for this astronomy applications. So there's 18 investigators across Australia. Actually, the centre will probably grow to about 200 people. We've got about 100 members already, so we're still recruiting. So if you're sort of looking for a PhD opportunity or a postdoc opportunity, let us know. Essentially, we've got now 6 years. So we've been running for about a year to try and make these frequency combs smaller, more compact, and working at visible, but also to look at what we can do with them. And so this is really why I'm here, is to see, okay, is there an opportunity to use these frequency combs for example, sort of imaging underwater, or for underwater communications? So the challenge with underwater is, here's just the sort of water absorption spectrum. I'm sure most of you are pretty familiar with this, that basically shows that when you're getting up to the infrared frequencies, the water absorption is many orders of magnitude more than it is down in sort of the blue, and it's sort of best down just into the ultraviolet, but blue. Now, why do we choose to use infrared in optical fibres rather than, because there is a little bit of water in optical fibres? The answer is because the Rayleigh scattering is the best. The reason the sky's blue is because there's a lot of Rayleigh scattering, and blue is scattered more than red, so you see more blue. This is also true in optical fibres. So you're sort of balancing the absorption of the water in the fibre with the Rayleigh scattering, and that's sort of best around about 1.5 microns. This also plays out in water communication. So if you're deep in the water where there aren't many particles, then perhaps you're better off with blue. But if you're in shallow water and it's turbid and there's a lot of particles around, you've got to know a little bit about your environment, and you might be better off with green or red. So the first idea is then, okay, if we were trying to get broadband communications, could we just use the same technique that we used in fibre in free space? We have shown that we can. So we've actually done a laboratory demonstration with 2 telescopes and shown that you can get, about 1 kilometre's transmission of the same data rate in free space. So that's so far so good. Could this be transferred to blue? And there's some examples in the literature where people have done something a little bit like that. So that seems to be a reasonable approach for deep water communication. Now, more subtly, what we might do with turbid water, the issue with turbid water is you've got the scattering, which means you lose light, but it also means that it sort of bounces around and you get sort of echoes. And so if you've got the light increasing as a pulse of light, by the time it actually gets to the receiver, it's bounced around so much that it's smeared out that it might have actually crashed into the next pulse of light. And so your communications rate is really limited by this sort of diffusion of light through this sort of turbid media. And so this is where I think some information processing, and particularly some adaptive information processing, could be beneficial. And so I've got a rather technical diagram here, but I'll try and explain it as simply as possible. We have one of these rings that we put a single laser line into, and what comes out is 100 laser lines. There's a sort of magic box here that allows us to control the amplitude and phase of every one of those lines. So we can basically apply weights to each of those lines. And where we were using those lines independently as communications channels, so each line has different information on it, now what we're doing is we're putting the same information onto all 100 lines. Then we delay them. So what we do is we put a set amount of delay. We use just a piece of optical fibre to basically put a stepped amount of delay on each of those different wavelengths. And what that allows us to do is basically take the same information, and if we look at the line in the middle, once we've done the delay, the wavelength sitting next to it is a little bit in the future, and then the next wavelength is a little bit further in the future, and the wavelength on this side is a little bit in the past. And so you can then have all at one time essentially the time domain shape of that pulse, and then you can process that by detecting it and applying all the weights that using these different this thing called a wave shaper. And that allows you to do filtering and phase manipulation. So an example we did nearly 10 years ago now was what's called a Hilbert transform, which allows you to sort of study the phase of RF waveforms. This is useful for radar, for example. And this just shows us that we can achieve if you put essentially a hyperbolic function on this, you end up with a flat intensity response, but a 90-degree phase shift on things. So this is quite a difficult thing to do in other ways, but we can program this filter to basically give us whatever response we want. We then went a step further, and this is a couple of years ago, and instead of using the different colours for the different delays, we actually put physical delays on a chip. And then basically dialed up the filter response that we wanted. But in this particular investigation, we actually sort of let a computer, or used an algorithm to adapt the weights that we needed on each of these different delays to give us the optimal response. And so firstly, that allowed us to, rather than having to canonically say this is the response we want and this is the Fourier transform of that response, the system could learn that. But it also adapted and overcame imperfections in the chip and the actual fibre system that it was built into. So you didn't have to. It actually gave you a better response than you would have if you just used the canonical thing. So there's sort of an element of machine learning. So the last thing that we did was actually use that technique and go one step further and actually have a second step. So we have had the weights that we could control to sort of put together a kernel. The delays allow us to sort of achieve a convolutional effect, and then another layer of light to act as a neural network. And so we were able to show that you could actually do pattern matching and classification with that system. And so I think the opportunity is to use something a little bit like that, use it with a green or a red microcomb, and then essentially try and unscramble the scattering that's happening with the turbid water to use all these different 100 laser lines to essentially reassemble the pulses that you achieved. And so this is something that we're looking at the moment. So, just harking back to the opportunities, lithium niobate, the platform that we work on, it will work at all of these different wavelengths and can actually wavelength convert. So one option is we can either have the lasers native at blue and green and red, and just as some examples of some of the chips that we've got in our lab operating at those wavelengths, but we can also use lithium niobate to take the telecommunications wavelengths and the combs that we already have and shift them down to those visible wavelengths. So this is my last slide. If you're interested in getting involved, feel free to make contact, and thank you for your attention.
Thank you very much. Thank you very much,